All right, so thank you all for joining the GCC May 2026 seminar. Today, Professor Mohsen will be presenting here with us. So the presentation will be like 45 minutes and then plus 15 by the end for some questions and discussions. But before starting, I would like to invite Professor Malcolm to introduce Mohsen. So please, Malcolm, go ahead.
Good day all. It's a pleasure to have you back with our GCC seminar series. Mohsen holds a special place for me. We've worked together. He joined me to assist me and then took over and now is the director of the JKMRC, which has been very pleasing to me. I'd say with Mohsen, it's really deeply inquiring mind. But he doesn't just inquire, he builds that inquiry on a foundation of knowledge. So you'll find whenever Mohsen's talking about something, he's read multiple books on it and articles and researched it on the internet. So nothing comes shallow from Mohsen. So when you ask him a question, he must probably give you 5 more back to you because he's studied it in depth. And this really has helped Mohsen develop deep insights and a connection to what is reality on site. So we've done quite a bit of practical work together, and is one of the people in my life when we get to site really gets what's happening inside the equipment and the process, how the process links together rather than just looking at a piece of equipment. And I guess that underlies where Mohsen's going with the research. And so it's really moving the JKMRC beyond the horizon that they were seeing into, where can we get to with a different style of knowledge, a different style of information and computational ability. It's like taking what Alban started in the 70s with a control system and completely rebooting it with what we have available to us now. So closing before Mohsen starts, Mohsen really gets a strategic view of where the value lies and therefore where our effort and output should be. So welcome you to Mohsen's seminar, and I'm sure it's going to be as fascinating as the seminars always are. Thank you, Mohsen.
Cool. Thank you very much, Malcolm, for very nice introduction and nice words that you made. I hope that I can live up to the expectation that you created for this presentation. So thanks everybody for joining the seminar, and I'm very grateful for a group of people actually joining this seminar. I'm very much looking forward to discussion after my talk. I will try to keep it to 45 minutes, as Tulio mentioned, so that we can have a bit of a time to get input from everybody. And I designed the seminar in a way that actually to kind of challenge some of the assumptions that we collectively have in terms of improving the modeling and control systems alone can help us to close the operational performance gaps that exist. And that, as Malcolm mentioned, come from like many years of inquiries that I had in my head in terms of why we are not achieving the performance that normally we expect, regardless of all of the advances. So this is some of my thought in terms of which is based on my experience and the studies that I've done that I would like to share today with you, and we can think about it a bit more in that space. So before I move further, I would like to first acknowledge the traditional owners of the land in which we meet and pay our respect to the ancestors, the descendants who continue their cultural and spiritual connection to the country and value their contribution to global society. So any lands that you are today joining us, I think it's worth thinking about the traditional owners and people that they have been living in those lands and their connection and their contribution, and value them. And as Malcolm mentioned briefly, I would like also to acknowledge the visionary founder of JKMRC that actually created a foundation that in my mind actually helped me and many people actually to get where we are. And also I would like to acknowledge the role of his wife Barbara as well, because as far as I could understand from himself, because I had a chance to talk to him in many occasions before he passed away, and the family that actually his wife had a big role as well in JKMRC. So I would like to also acknowledge this great person that actually had a big contribution to our industry as well. So I think because I'm going to talk a lot today, and it's going to be a bit of a mix of practical and professorial and lectures as well. But I think one point that I want you to not to forget, and that's probably my key message in here, is the system that we model for our optimization efforts and process control is not the system that actually is being operated. That's my key message in my presentation, and I hope I can essentially, by the end of my presentation, give you enough examples and enough background to essentially to challenge that assumption. And essentially, the comminution circuits that we are operating, it essentially is done, the operation is done through continuous negotiation, identifying trade-offs, making decisions between those competing objectives that often actually happens behind the back and outside those control systems that they include our models and our advanced automation. And the rest of my slides, I want to kind of establish this point, and I hope that actually at the end, I can briefly explain about the solution that I'm proposing and we are developing in the JK, and I would be keen then to hear your thoughts. So in many cases, when I get the chance to look at the operational data over extended period of time, and this graph that I have here is one example from one of the operations looking at the feed rate of the SAG mill over 2 years per production line, and that's across 3 different lines. We see that actually, despite all of the advances that we have in model development, lots of essentially advanced tools that we have in our control system, the model predictive control, advanced process control, in recent years, AI and digital twins, and all of those technology, is still we are losing lots of opportunities. As you can see in this graph, there's a big portion of throughput in the plant that actually is way below the target and the sweet spot. And in my mind, if a control system is doing what it's supposed to do, and essentially it's trying to optimize the process, it should be able to maintain at least a significant portion of the time, maintain the process within that boundaries that exist, and we define it as an optimum system. And the question that keep coming back at me is why that happens. And the question that I had was actually started looking into many aspects, looking into the quality of the control systems, the quality of the models, and all of that. And no matter how sophisticated you develop your models, how advanced you go with the control system, still you end up in these type of situations. So the example in here actually is from one of the operations that they have, essentially arguably one of the most advanced control system in South America. And they had all of the dashboards to understand what's happening in the process, immediately inform the operators to make decisions. They got the most sophisticated APC systems to monitor and control the SAG mill. Still, they lose significant amounts of opportunity in their operation. And this is one of the metrics. When you look at many of the metrics across the operation, there's no better than this situation. So that essentially one of the key points that actually we consistently see a persistent gap that exists between what is the predicted performance and what is the realized performance after operation. And that essentially, to me, drive me to the conclusion that actually the system that we modeled and we embedded into our control system and we try to optimize based on those models are not technically the same as the operated systems that we normally have to run. And there are several aspects, if you think about it, that actually they are different. So when you think about the design or model system that we have, often we have a fixed constraints around the process, which is coming primarily from the design and operational limitation. We tend to think that actually we have preset or optimized situation or objectives that actually we can model them and our models can predict them. And then optimization that is very explicit and it follows generally all mathematical models, the boundaries of the system that are well defined, and the state of the process can be easily defined through mathematical equations. But if you go deeper and look at the operation in reality, especially like as Malcolm said, and as we sit in control rooms and spend of time with the operators, you see that actually the boundary and the constraints are always negotiated by operators across different units. The priorities keeps shifting depending on equipment availability, maintenance requirement, sudden breakdowns, changes in operational plans, changes in priorities. Then the optimization is not as simple as a models that they have to achieve an optimum. You have to always work out the trade-offs that happens. Whether you want to now look after your high-grade tailing that comes on one end, or do you want to achieve the throughput? Or you essentially have to look after the chemicals that is not ready to be essentially set to the flotation cell, and many of those trade-offs that operators have to think about it and then reset the priorities. And then the boundaries also always are changing and depends on the context that they have to operate. They have to redefine the boundaries of the process. The equipment availability, the ore availability, the mine situation, your flotation downstream, and all of those keeps adapting, requires adaptation of the boundaries. And also the state that the process is in is not purely technical as well. And I put this term socio-technical because in many cases, the individual preferences, the situation that they are in, some of the essentially human interaction and human essentially level concepts also defines what state the process would be, and also the definition of that state as well. So in real operation, essentially, we have many critical decisions that still rely heavily on human negotiation across the teams and functions. And that essentially means what we have modeled and what we have designed is not necessarily comparable to or it's not necessarily the operation that in real operation we run them. And that's for many of those reasons. Also, when you look at the APC and MPC, although they are very powerful, and now they are very well formalized in our processes and they have been in application, but they have certain assumption that underpins those models that it essentially makes them very limited in terms of how they can achieve optimum solutions. So if you look at a typical MPC strategy, similar to the graph that actually I adapted from a Sparborough book, you will see that actually there are explicit models that is underpin the MPC system that essentially predicts the behavior of the process or models the behavior of the process. Then it assumes that actually you can predefine or preset those objectives that the process has to achieve. And then the other assumption is you can actually, with the help of the measurements that you have from the process, you can measure and estimate the state of the process. And also, you know how the manipulated parameter or controlled variable could change the behavior of the system and what are the constraints. And then one of the other key assumptions is you can sufficiently predict the process over a certain horizon. So in a shorter term, over the control horizon, and in a bit longer term over the prediction horizon, to be able to understand where would be the future state of the process. In a shorter term, you start acting in the control system in a essentially much faster. And then in a longer term, you start estimating the projection and start planning in terms of what are the manipulated systems that you need to adjust, and start preparing your control system for achieving those set points. So essentially, many of those assumptions that APC and MPC systems they have, and they are working on based on that, they are not hold necessarily when the real operation kicks in. So the key assumptions that APC and MPC expect to have is define objectives, constraints that they are not moving and they are stable. The relationship that we put on essentially as part of the MPC are representable, and also the behavior of the system is predictable, at least within that envelope that we have, whether it's the control horizon or prediction horizon. But in real operation, at least, this can be argued with any other type of operation, but I can conveniently say for mineral processing that ore is completely different in terms of the behavior and keep changing. despite that we like to believe that actually from the geological information and the limited samples that we got, we know our ore body very well and we know how it behaves. But in reality, we don't know about that ore at all, because that ore is for the first time that comes to our process. And necessarily, similarity in geology doesn't mean that actually is going to behave the same. Then the priority, whether it's downstream or upstream, constantly shifting. The interaction between disturbances, it's dynamic, especially when, for instance, combine the equipment wear, liner wear of your mill, changing dimension of your cyclone, changing behavior of your pump because of the wear, change in your texture of minerals as the circulating load evolves. The operators that they keep adapting the process based on the information that they collect constantly from the context that they are operating with, the constraints that they adjust, and also the trade-off between objective. All of those actually defeats the assumptions that APC and MPC, they tend to work. So therefore, if you think about it, in reality, the optimization problem that we give to the APC and MPC system to solve, it's a evolving problem all the time. So let's look into a few examples. This is an interesting one to look at it. So I have a few case studies that I collected from some of the works that we did in the past couple of years. And some of them actually, at the time, I was very naive and thought that actually, okay, with good models and with good analysis, we would solve them. And then I started learning more and more and reading more about the concepts that I'm presenting today. I started realizing that actually why we couldn't get to answer and probably some of the reasons there. So when you look at the APC system, a typical SABC circuit, the SAG mill, ball mill crushing system, I intentionally put it in this form. So essentially you have a number of units that they connected to each other, circulating loads that they come back to different units. And one would think actually, okay, this is very good. If I have a good ball mill model, good SAG mill models, good cyclone models, and we have plenty of them, and people in this room, in this meeting actually have been working for many years to develop these fundamental and semi-fundamental and improved models as well. So we can put them together and we can essentially start predicting how the system behaves. But in reality, it's not only those units that actually their interaction would be complicated, but also all of these other peripheral systems that exist in between as well, that adds to the complexity. The control loops that they are working in each of these systems, sumps, pumps, piping, and all of those also adds another layer of complexity. So in reality, the whole process that we try to operate and simulate is not as simple as I will break it into subsystems, I will well define each of the system and put it back together, and it's going to work very predictably. It's a very complex system. And let's look in few examples. Ball mill overloading, I think Malcolm is here. I'm not sure if Marcelo is around as well. We have been discussing this one for many, many years, and it's one of the big challenges in our industry. People, they are very keen to know when the ball mill is overloaded. So we have been commissioned by a group of one mining company to start looking into that situation, and through some study can be identified ball mill overloading. And as you can see, a couple of examples here, people have been working in this one as far as 1991, developed some essentially arbitrary numbers, some workflows to be able to go through the system and identify ball mill overloading, and they haven't been successful. We attempted it with the data analytics approach, tried to look at the data, use our essentially clustering algorithms and data analytic tools to identify different operating regimes, like when the power draw drops suddenly or the load start increasing significantly, defining essentially some confidence to each of those ones. And then we went to a very sophisticated process to interrogate and isolate 2 years worth of production data into all of those different operating regimes that could signify a ball mill overloading situation. And then with discussion with the site people and our knowledge of the process, try to isolate potential factors that they can contribute to ball mill overloading. And as you can see, these are essentially the volume plots and frequency distribution of different operating states, trying to see if any of the individual factors like sag mill power draw, pebble generation, bond work index of the ore, or recirculating load, the percent solid of the cyclone, could actually demonstrate whether they are contributing to ball mill overloading or not. And it wasn't successful. So, and to me, at the time, I couldn't really understand why, but now I can tell you that actually by understanding the concept that actually we are inherently dealing with a complex system, and it's not easy to implement a reductionist approach and be able to isolate the role of each individual factor. What this data tells me essentially is the ball mill overloading is not a result of a single factor that might affect and creates that situation. It could be an interplay with many of these factors that is not as easy to essentially isolate them and identify them from the data. Another one is about the sag mill operating states. Again, we've got lots of experts around the world that actually, some of them are in here, that they spend, I could say, their life around looking how the sag mills are operating, trying to look at many factors that actually affects the sag mill operating state, whether it's overloaded, whether it's underloaded, and whether the ore is very hard, is it slurry pulling or not. So we thought that actually, okay, we got one of the best segment models, why we can start combining that with some operational data, especially with our process knowledge. Marco, my colleague, is here today, so he has a very good knowledge of the sag mill model. He knows which are the factors that are actually affecting. So we got our PhD student, Niranjan Adhikari, say, okay, you are a data analytics expert. Let's start doing the clustering, identifying different factors, relationship between factors that exist between ball mills, between sag mills, and let's see if you can identify the states of operation. And then we went even one step further, and we got experts around the world, 6 of them, and say, okay, we got these data clustered. Can you guys also look at them and see whether they are signifying a specific type of operating state in sag mills? The result was interesting, but not consistent. And again, the outcome of that to me was actually the data that we have. It's not very as easy as, okay, I can actually cluster them and start finding one-on-one interaction or even interaction between multiple factors and then easily use that to say this is the operating state. So it means that actually, again, the reductionist approach in here in terms of isolating sub-mechanisms that happening inside the sag mill, and then understanding them very well from the data and putting them back together is going to help us to understand how a sag mill is operating and what's the state as well. And it's a very complex process. And the very last one is essentially the liberation. And again, in this room, I'm honored that actually I have many people actually, they have walked their life around liberation as well. And again, my argument here is actually liberation also is not as simple as a size-dependent property. Actually, is a process-generated property. An example that we have is the work that actually we did in JK, and there are a few examples before that, like Malcolm and one of our ex-PhD student, Juanjo and Kim, they've worked on that as well with some examples, that when you combine a grinding circuit with different modes of classification, despite having the same feed, same product size, you see a significant variation in liberation of the material. In this case, for instance, what we did was in a very controlled situation in our pilot plant, we grounded material, and then we did 2 pathways for classification. One was cyclone, another one was combined cyclone and screen. And then, to our surprise, we got significantly higher liberation for the same grind size, for the same size range. And that again means, despite we know very well how the materials are going to break in mill, how they're going to behave in our cyclone, how they're going to behave in our screen, that doesn't mean that actually in terms of the response to texture change and liberation is going to be always the same. And the interplay between those factors can change the response of the system. So all of these actually, it introduces a concept that I want to, in the next 2 slides, to briefly explain it. And that's the emergent behavior. So the emergent behavior is very well known in system thinking and complex systems. So essentially what we know is there are certain behaviors that even in a very well-defined systems, they emerge without us being able to predict them or essentially know where they're coming from. So Marco has been using cellular automata for stock pies, and to my surprise, I found that actually the very first introduction of cellular automata actually was around the concept of emergence. So essentially, you can see a couple of examples in here. That is a very famous essentially concept called game of life. There are very simple rules around the cells that you have in an environment. So those rules are fixed, and all of the cells, they follow the same rules. There is no global controller and there is no central optimization. But depending on what you put in that system, you get different type of behaviors that often they are very unexpected. And a simple change in that environment suddenly might change the whole behavior. For instance, these patterns, when they come to that fixed rule, they call still life. They don't change, they don't move at all, and they stay where they are forever, unless you do a single change in that environment, which might change the whole behavior. There are certain patterns that they call them oscillators, that they keep essentially evolving with the same oscillation. Again, the same rule applies to all of these patterns, but you see a different behavior. And there are another groups that they call them gliders or moving objects that as well, that when you create that pattern with the same rule again, they start moving across the environment. They might come back to the original shape, or they might reshape together, and essentially they create that. So essentially what you see is in a system that is inherently complex, having fixed rule, well-defined boundaries, no global controller optimization doesn't mean necessarily results into a predictable behavior, and it can actually change the behavior as well. And that's essentially the concept of emergence. And normally we deal with two types of emergence. One is actually, I'll call it interaction emergence, type 1. And another one is called pathway or adaptive emergence. In a philosophical world, actually, they have two different terms. I wouldn't use them in here, but in the references that I shared before, later, you can actually look at them as well. I try to put them in our concept of mineral processing to make it more sense for us. So when you think about the interaction, for instance, the example of liberation that I mentioned, when we know how the breakage of the material in silk device or our breakage device can result into certain texture, and then when we put it in our cyclone model, we know how different densities and texture they're going to end up in overflow and underflow. We would think actually, okay, we know the rules, we know our mill. If we put them together, we should be able to predict how the system is going to behave. But what we can't predict is the interaction between the mill and cyclone that might change the result that we get from that ore. And it's not going to be always the same as well. It depends on what type of ore, what type of classification, and what type of grinding. Even for the same ore, the change in the grinding, change in your rheology, change in your circulating load, all of those can actually change the response that you get with your system. And that's generally is qualified as interaction emergent. There are certain other emergent around pathway adaptation or adaptive emergence as well. And that's mainly around essentially the changes that happens in the system along the way that might also change the behavior of that system as well. And for instance, when we know that actually when the liners of the mill start weighing out, the response that we get from the mill, it keeps evolving as well. Some of that is easy to model, but some of those in essentially evolution of the system, it creates unpredictable behaviors that often we scratch our head and say, oh, why our model doesn't predict that? And we think our model is not that good. But I think some of that actually can be qualified as emergent behaviors that actually is not very easy to capture in model as well. So those are some of them that exist. So essentially, the grinding circuits, my argument is, are not only controlled system, but also they're adaptive. So it means that we have to be ready to accept the fact that actually there are emergence that happens within the grounding circuit that is not easily captured in our models to be able to essentially put them into our APC and MPC and then use them in that form. So essentially, one thing that I want to make sure that we get it, when I talk about emergence, and I put a LinkedIn post before, and then somebody came and said, oh, this is very scary, than not being able to predict. The emergence doesn't mean chaos, doesn't mean randomness, doesn't mean lack of physics. And if we make our physics best, then we can capture them. And it doesn't mean it's impossible to model as well. So to me, that's one of the key points. And later I will show you my thinking in terms of how we can actually manage those, because these emergent essentially is a concept that has been in philosophy for many years. People have been thinking about them, and they come up with ways and methods that they can actually deal with them as well. So, but one thing that we have to understand is these are essentially the behaviors that emerge from the system, and doesn't matter how well we make our models, how sophisticated we can develop our models, and how much we can improve our models, we should expect that these might happen. And in my argument, based on what I've seen so far, is bulk of our inefficiencies and bulk of the reason that we cannot take out operators completely out of the picture and leave a control system to make all of the decision is because of these emergent behaviors that are inherent in our systems. So and to me, that's the point in terms of when we get to automation and decision making, pretty much automation stops where actually real decisions are made. So automation in general is designed for stable processes. It's only set for execution optimization logic. It follows constraints and boundaries that are well defined and tries to maintain a predictable operating essentially system. Whereas the real decisions happen when things are not following those essentially pathways. So when the conditions are changing and somebody has to interpret those changes, and that's essentially purely from the emergent behaviors. The objectives that have competition and you have to negotiate and make decisions there. When information are not complete and they are missing information, we know that actually in many cases sensors are not calibrated, sensors are not coming essentially online, many data that is not available to make decision. We don't know exactly where the ore has been mined or how much has been in the stockpile. So all of those incomplete information, this control system is not designed to make decision based on incomplete information, but operators, in any case, they're going to make essentially an educated guess. And those are the cases that actually, in my mind, when you want to start really operating the system, you need to make those decisions, and that's where the automation essentially stops. So when you want to optimize your process, necessarily is not a process control challenge, it's an operational decision that you need to make. And that's where, to me, the hidden operation layer comes into play. So when you look at your physical process, you design your control system to essentially measure and optimize some, I call it physical matrix, like throughput, recovery, energy, process stability, that those are easily modeled, and we think that actually we know where they have to head. But when it comes to a real operation, there's a layer that operators are there and they make consistent decision making and they guide essentially all your physical system. And that's where the automation stops and the decision making kicks in to optimize the process. And if I put them together in a systemic view, you have IT system in a control system, you have your operational technology, and they are very well advanced. We got all of those systems that I listed in below for even plant-wide optimization. But in reality, we have a missing layer in that system. And that's where the operator sits and makes those negotiation and trade-off and decision-making. And again, I want to loop it back into the concept of emergent. This is not simply because if we make our models much more sophisticated and advanced and make our systems well integrated, we would be able to solve the problem. Those are inherent issues, behaviors that exist within our circuit that needs that decision making to be able to optimize it. Our industry actually moving toward that direction. I think it's a significant effort has been made, and I was in a Honeywell presentation 2 days ago, and I've been talking with a group of people, especially the AI specialists that they have been there, and most of them, they are aware of the gaps that exist when it comes to plant-wide optimization, and they have been doing lots of these attempts. But I think although they are a big step ahead and progress, but still they are fundamentally assumes that the objectives of the system can be explicitly defined, and the good models and sophisticated models are able to predict what's happening in the process, and they can be used. I think that's the fundamental flaw that I can see in here, or the gap that I can see in that approach. AI, I think everybody now have heard lots of that. There's a big excitement. I was talking with few groups that actually they're pushing AI hard, and we do it in JK as well. And again, the current approach is, okay, we're going to have these AI that they are developed, especially now the buzzword is not even AI, it's agentic AI, or some people, they call it agentic AI. I think the US guys call it agentic AI. So there are specialized optimization agents that you can create. You got domain specific experts that they can train by books and the data and all of that. And I've seen one example 2 days ago in Honeywell Group. And then the data-driven coordinator. And then you put all of them together. You have one master at the center that is an operation-wide AI expert. And they can understand what's happening in the system, and they can help you with that. Again, this is a big step ahead, but the system still fundamentally assumes that operational objective can be defined explicitly and optimized explicitly. And again, if you look at the concept of emergent and the examples that I mentioned and the reason I provided, that's not as easy to do. So essentially what we need to do is we need to start rethinking. So we should move from the reductionist approach, which is the fundamental to our approach in advanced control and the way that we design our modeling and optimization, to a hybrid approach. I'm not saying that actually the reductionist approach has to be completely removed. That's work into the certain level, and we need that. But also we have to start thinking for the real operation that actually operates in a different area, and we have to start moving to that direction. So when you think about the fundamentals of our control system, we think that the process is highly regulated. That's fundamental to our reductionist approach. And that's, if you remember the MPC system, it thinks that actually, okay, are going to be able to predict the behavior of the system within that horizon with all of the variability. And also, it thinks that the objectives are either known or preset or can be modeled. But the real operation, actually, the behavior is not always consistent. It's variable. It keeps changing. The emergent that happens that is not very easily to model. And when that happens, in reality, essentially the objectives are not well-defined, predefined as well. And you have to rethink and renegotiate those objectives. So the question is, if that's the case, can we design an automation system or a decision-making system that, instead of trying to always chase targets that are dictated by models, can negotiate those decisions the same way as our operators? So essentially, my question was an automated system that can negotiate operational decisions in the face of uncertainties, in face of conflicting objectives, in face of incomplete information. Is this possible? And essentially, my argument is yes. If we look enough into some of the work that happened outside our domain, especially in philosophy, when they are talking about the differences between complex systems and essentially systems or defined systems. And a bit deeper, it's a big debate between essentially Hegel and Kant at the philosophical level. And in my mind, actually, it's not either of them. It's both of them for us in application. So the answer is yes. Essentially, we can use AI in a different way to help us to essentially move away from model-driven optimization, or combine it, not move away in a sense, augment or advance our model-defined optimization with a negotiation-based decision-making. And that's where the AI actually is best suited to do that job for us. And the way that I'm proposing is we use AI as a moderator of a negotiation instead of being a knowledge holder of the whole system or a god that learns everything from the data, and try to bring all of the key stakeholders to the negotiation and then do a negotiation-based decision-making when things are not following our modeled system. So in a sense, what I'm proposing is a hybrid approach. So we maintain our system thinking approach for subsystems, but when it comes to understanding the emerging behavior of the system, we switch to that complexity thinking and we start doing negotiation. And this system actually is a way for us to integrate our OT and IT with that hidden decision layer system, which essentially incorporates emergence, incorporate negotiation, and keep adapting the boundaries of the system and the definition of the system, and then provides a target for our APC and MPC system to achieve that. And I call it communicative process automation in a sense. So that's an added layer that actually, instead of trying to follow predefined paths, it communicates the decisions and then finds the best optimization and then pass it to the control system. So this is a very early step of the concept that I'm putting together. The idea here is actually we still use the buzzword of the year, agentic AI, but in a completely different way. In here, we are not training AI from the operational data to be the knowledge of the process to be able to start negotiating. We are training agents that they are specialized in one process of decision making. I mean, the other day I was making an example with to Malcolm. So if you be able to copy the brain that Malcolm has, so he goes through certain steps for making a decision when he sits in the control room and tries to control a SAG mill. So essentially what we do is we use agents that each of them, they are specialized in one task that a typical brain do to make a decision. But each of these agents are trained based on science and knowledge that exists around the decision making. There are a few of them are here in terms of like discourse agent, evaluation agent, consensus synthesizer, and each of them, they have their own task. This is by no means a final concept that we have. At the moment, we are working into what's the minimum number of agents that we need, what are the essential skills, and then what needs to be improved. But in reality, the role of this essentially CPA layer is not to be the knowledge of the system. It's a decision making expert that, regardless of what's the process that you're dealing with, can connect to your process through that interaction hub, can easily integrate the human expert into the negotiation, as well as all of the other components. And then every time that there is emergent behavior happens, it kick off a negotiation process, the same way that an operator would do that. But in this round, or in this way, instead of human making inconsistent decisions and not being able to access to all of the information and process all of the information, it consistently goes through a process that is well defined and well structured and is consistent, as well as it will interrogate and access to every data that is important. So then the decision should be much more improved compared to the decision that human makes. And then those decisions sets the target for the APC system to follow. So in that sense, essentially what we do is, instead of trying to force the control system to blindly follow preset target or what the models say, we keep identifying where is the real process now, what is really achievable, which is through that decision-making process, and then we pass it to the system to follow. Behind the back, there are a few mechanisms. I wouldn't go into much detail of that. I mean, people, they can read them later if they are interested. But we use Jürgen Habermas as one of the core in our essentially process around how the decision comes to fruition through the communicative action process. And also we use Michel Foucault's power dynamic to make sure that different parties to negotiation, they don't always come with the same power, but they might have a different weighting in terms of the influence in the decision making. And inherently, these two layers, they can work hand in hand. So essentially APC and MPC system, they look at those fixed models and they follow the known trajectories. But in APC, what we do is we keep debating those dictated boundaries and targets, identify what is achievable in the face of the emergence that might happen, and then we pass that direction to essentially APC to follow, instead of forcing them to follow a blind pathway. So very quick to keep my promise. So a takeaway, I think, to me is we need to think about optimization and automation essentially differently, I think, instead of just having a fixed optimization idea and trying to keep improving our models, which is a good thing to do. And we have to continue that. We have to think about probably there is a bit of a gap as well. So the model development and improvement and advancement in APC alone is not going to fill that gap. And to fill that gap, we need to think about adding a decision-making layer at the top as well. Essentially, to me, what I'm proposing is not a replacement, it's a complement to fill that gap that exists. Emergent is an inherent property of our system that we are dealing. So we cannot expect that actually we can model mathematically all of those behaviors. So therefore, having a mechanism to be able to identify them and then be able to set the new targets in the face of emergent is important. And essentially the communicative process automation that we are proposing probably is one of those pathways. And I'm hoping as we discuss this, other people, they come up with different ideas as well. So I have series of posts on LinkedIn. If you're interested, you can actually look at those ones as well. I'm very happy to continue the discussion here. And then later we share the slides. So I have range of references that I had the fun to read them, and I thought I would share with you guys as well, so you might actually enjoy reading some of them as well. So, and I think with that I will thank you for your patience, and I'm happy to answer questions. So I'm 2 minutes over the time, but not too bad.
Thank you, Mohsen. Very nice presentation. Thank you for that. And yeah, so now we have time for some questions. And if you have it, just raise the hand or open the mic and speak up. I think we have 2 questions. Is Stephen first?
Stefan.
Yeah.
Stefan.
Hi, Mohsen. Fantastic presentation. Thank you.
Thank you.
I never thought that I'd listen to a mill circuit presentation that mentioned Hegel and Kant. That's fantastic.
Yes, I'm very sorry.
Brilliant.
I think
Absolutely brilliant.
they also
love
would be very disappointed. Say, oh, how it comes the mineral processor talking about us?
Yeah. I was just thinking about within we have a team who works on application of AI into process control, process optimization. And they've kind of taken the approach of making recommendations as opposed to trying to control the process as an agent as such. Is that something you've thought about, of actually trying to create a system that's complementary to existing operators and providing recommendations as opposed to taking over the process itself? Do you think that's a potential pathway?
Yeah, the CPA essentially at the start, it's going to be primarily recommendation system. Essentially, through the negotiation, identifies potential pathways for operators. But the idea here is to get the input from the operators as well and incorporate it as part of the decision making, and then provide the decision with the rationale and essentially the confidence or potential consequences. Because again, despite, I mean, at the moment, that's my idea for now with the amount of knowledge that I have and the level of the tools that actually I have developed, that actually they might not be able to capture all of the context. So therefore, still we need human to balance some of the potential risks or the knowledge that they have that they might not be easily captured in our negotiation process. But if we can actually advance them more and more, we might be able to do that. But one thing that I think we want to avoid is actually, or we want to help, is the inconsistency that exists in decision making by operators depending on their knowledge, their preferences, and their experience, to make it a bit more consistent. And the approach that generally at the moment industry taking in terms of using AI to be trained potentially behind the back by some of the decisions that operators make or from the data is a good approach. But my reservation with that is still we are assuming that the whole knowledge of the system exists in those data, whereas the emergent behavior is not captured in those data. The other problem that is inherent in that approach is actually the scalability, because every time that you want to move from site 1 to site 2, you have to go through the same process of essentially collecting the data, cleaning the data, and training your AI, which make it very expensive and hard to implement. Whereas the system I'm proposing is a decision-making system that doesn't train to any data from operations. It is trained for decision making. So essentially, it's scalable or easier to scale in terms of moving from one case to another case to another case, because we don't change the decision making process. We just move it between different processes.
Marcelo?
Yes, fantastic presentation, Mohsen.
Thanks.
Well, have a lot of discussions that I like to have with you, but in a few months we'll meet in Italy, I suppose.
Yes.
As well. I think some of the nice messages that I see here, obviously, is that I think we have to be careful with AI in the end of the day of not really replacing all our knowledge even in a particular plant. Remember the fact that the AI is actually reproducing what was already happening in the past, but we sometimes really want to explore different domains of operation, and that's exactly where the models come in, and I think we have to improve the models in that direction. But I think it's really a nice structured way to really rethink the process, really identify that I fully agree that the models will, even dynamic models and really fancy models, they will have limitations. And the limitations can be filled by really this type of understanding and really filtering out, I believe, the information. That's what you do. I think really fantastic work. And yes, what we know from Comminution is that if you increase the specific energy, you definitely get a final product if all goes well. But beyond that, I think the interactions become really, really obvious, isn't it? That we know rheology, as you mentioned, and so on, and we don't measure everything. So it is interesting, really, I suppose. This structured way that you're looking at is to actually filter out and to really understand that we have background knowledge from experts and we have background knowledge from good operators that cannot be thrown away. Because what I'm concerned with, as many people, is really to not really start to underestimate the importance of knowledge in favor of AI, which is happening in some areas, isn't it? And I don't know, call centers and things like that. I believe it's a done deal. But in operation and in processing, it's definitely far from that. So it is really a good structured way to show that this is the path forward, and be careful of not trusting either one. Too much models, APC, and too much MPC, and not too much AI.
Yes.
Fantastic.
Yes. I mean, very good point, Marcel. I think one of the key points that I want to emphasize as well is, as you pointed out very rightly, the models still, I mean, my suggestion actually is we shouldn't stop developing models. We have to develop our models. We have to advance them as much as we can. But as you pointed out as well, there is a gap or essentially between what the models can do and what the actual system is. And my point is that gap is not possible to cover it with models. That inherently is the property of a complex system, which needs another layer to be able to address that. So the better our models are, it means that our APC and MPC, they're going to do a better job. And then, to me, once we fill that gap with the help of our essentially system that tries to negotiate and understand the system, then we can always provide key boundaries and information that our models are in need to be able to do a better job. And many of those complexity that is not easily captured in the model. So essentially that negotiation layer, it can identify them and then say, okay, now the boundaries that you were thinking or the objective that you were thinking in the model now has to be in this space. And then the model, the better they are, they can do a better job in terms of, okay, what manipulation model parameter, if I change, I'm going to get to that response faster. And then having a better control system is very valuable as well, because then they can actually be more active in terms of, okay, now I'm going to get you to that system much more stably and get to that point. But if we don't have the negotiation layer, the issue is the models are constantly working toward a fixed target and objectives. And that's where we see that actually they try to push the system, it doesn't get there, and then it causes instability. And that's essentially, to my point, is when we add that is going to be the point. One key point that you mentioned, which is very important again, the experts and the human. Doesn't matter how well we try to capture everything, we are not going to be able to get all of the context that the human expert can do that. So one of my key essentially challenge with some of the OEMs that they were talking about the concept of light off control rooms or essentially man out control rooms, essentially was, no, you can't get there. We need human because there are certain contexts that only human can capture from the environment. Even with the system that I'm talking about, still I cannot have all of that. And in my structure, actually, as you can see, I have a human expert as one of the inputs there that always is going to have input into the process. The only thing that I do is I say, instead of giving it to human to make the decision or drive the decision making, we make it part of the process. And then with the help of the power dynamic and some discourse agent that actually is going to check the validity of the claims and the experience of the operator, we don't always give a high equal weight to operators. We bring that context and then we put them in a correct way as part of the decision making. So essentially we make it much more efficient in terms of how we get the input from the human to be part of the decision making as well. But I fully agree with your point, but definitely we're going to have lots of discussion very soon. Pekka, over to you. I'm ready to hear you. Good to see you as well after a while.
Yeah, great. Thanks, Mohsen. So really good stuff and a really like eye-opening topic. I need to maybe defend a bit of the APC side of the industry because I'm nowadays representing that. So I agree that there is a kind of potential, hidden potential that we need to capture in one way or another. I'm bit kind of against of saying that APC is flawed or cannot address that. There are APCs and then there are APCs. So I'm just saying this because as a company we have provided APCs for 35 years, and we have had a great success with that one, and in some cases we've been able to increase the SAG mill throughput by 20%, and with 99% level on or system being on automatic, so it is almost autonomous system that we've been able to do. And how we have been able to do is that actually there is APC is not only model predictive control, so that is one of the methods in toolbox. So how we bring this kind of decision making under uncertainty element is that we are using fuzzy logic on top of the top layer to provide the real-time optimization essentially kind of modeling the world's best operator, be it the Malcolm Powell or someone else. So our systems work in that way, and we've had a great success in that, and it kind of addresses the same thing that you are trying to address here, but in a bit different way. And I'm just saying that, you know, we are now living in AI hype, which is kind of phase 3 AI hype. So in the 80s came expert systems that were supposed to kind of replace all the workers. Then it kind of died, and then next big thing was the neural networks in the 90s, and now we have the LLMs, which is kind of phase 3 of the AI hype. And you know, I'm just saying that the expert systems and fuzzy logic are essentially doing quite similar things that what you are suggesting here. So maybe worth looking that one also. But all in all, really good stuff, and really happy to hear what you're presenting here.
Yeah, thanks, Pekka. Thanks for defending APC and MPC as well. So, I mean, I agree with you. Like my point, if it comes across as these systems are flawed, is wrong. So I didn't mean that. But my argument is actually there's a limitation to what they can do, and what I'm suggesting is filling that gap. But I agree, no, they are not fundamentally flawed. They are designed very well for what they need to do. But my argument is there is a gap there. With the expert systems and fuzzy logic systems, again, they are essentially adding another layer to the APC MPC system that actually they can help them to not follow strictly those models, and they can manipulate some of the boundaries to a certain level. But to me, again, because those are based on the rules that you identify or the relationship that you identify. The key point is the emergence that happens in a complex systems are not, as I mentioned, that game of life. So it's not rules that you can actually then capture them as part of an expert system or fuzzy logic system. Those are the behaviors that come about when things start slightly moving in a different direction or changing in a different form, and then you see that emergent behavior. In my mind, that's where the negotiation or CPA layer kicks off, in terms of we don't have to constantly run that to find and replace the APC and MPC. The APC and MPC, they can work to a great extent. When those emergent happens, that they are quite often happen, then we kick off the new negotiation and we guide those systems underneath in terms of maybe now, because of the change that happens in the system boundaries and the condition, you need to essentially reconsider some of the targets or the boundaries that you need to do. Essentially, it's working hand in hand with those advanced systems, but guide them slightly to the right direction. The intention here is not about, okay, these other systems, we don't need them. Actually, the more you have, the whole success of the process is going to be even better, because those advanced systems are the backbone of what I'm proposing as a communicative layer on the top. But if I came across as these systems are flawed, I'm wrong, and I apologize for that. No, they are not flawed, but they have a limitation. Cool.
All right, so
and
thank you,
I think don't try to replicate Malcolm, but I think all of your computers, they're going to break, because Malcolm brain cannot be replicated, I think.
Okay, thank you, Mohsen, for the very nice talk again. And thank you all for joining and for the interesting discussions. So we'll see you in a month's time. So thank you all for joining.
Thanks, everyone.
Thanks, Mohsen. Thanks, everyone.
Thanks,
Cheers.
everyone. Bye.
Thank you. Have a good time.
Nice seeing you, everyone.
Thank you. Goodbye.